Hello, everyone. Welcome to our webinar about AFM-in-SEM LiteScope and how it redefines the In-Situ Correlative analysis. I'm Veronika Hegrova, Application Manager at Nanovision. And today I'd like to, first of all, talk about the AFM-in-SEM technology, about its key benefits and the capabilities. I'd like to introduce LiteScope and its key features and what is the package of LiteScope. And I'd like to focus on the application examples and the overview what we can do. And afterwards, summary with Q&A section. I'd like to motivate you to ask questions in our Q&A chat. My colleagues will answer it right away. And so it's best to ask during the webinar right away. So who we are? We are a Nanovision company located in Brno. It's an exceptional place where many universities and research institutions are. And we have quite strong microscopy community as Thermo Fisher Scientific Division is located here. Tescan Orsay holding DeLong instruments, many smaller companies and research institutions like Masaryk University, Brno University of Technology, or Central European Institute of Technology. And so this is how the AFM looks like. It sits on the SEM stage. And if we have a look at the image or recording inside the SEM chamber, this is how we see the images. But before we get to the details, why AFM in SEM? So both of these technologies are complementary. So AFM can measure precisely the 3D topography, high resolution in that direction, mechanical, electrical, or magnetic properties. On the other hand, the SEM is great for fast 2D imaging, bigger overview, and surface modifications by other techniques which are there, for instance, focused ion beam or gas injection system, or other detectors for elemental composition or crystallography structure. So if I should point out some of the benefits, it's definitely in-situ sample characterization, correlative multimodal sample analysis, and precise location of the region of interest. So this combination helps to provide to create hard to reach analysis or otherwise unobtainable information about the sample surface or very time consuming. But what these words mean, or what do we mean by that? So in-situ characterization with LiteScope in SEM chamber, it enables measurements in one place at the same time and under the same conditions. So there's no need of transferring the sample, or we are sure that there hasn't been any contamination or oxidation because of the transfer. Correlative sample analysis by us means that we can benefit from both AFM and SEM technology by measurement simultaneously different signals or one by one within the same chamber. So we can measure SEM, surface potential, topography, magnetic domains, all we can correlate into 3D images. Regarding the precise location to the region of interest, thanks to the SEM overview, it's quite time efficient and easy to see the very end of the tip and find, for instance, nanowires like this. So measurement of hard to reach places become possible. Further, we can unparalleledly control over the probe or over the experiment, so we are sure if we are doing what we want it to do. And as I was talking about the CPAM technology, simultaneous acquisition, how it actually works. So we have the AFM probe approach to the sample, and we switch the E-beam from scanning once we are in location to the spot mode. So afterwards, we start scanning with the sample, and we obtain XYZ direction, XYZ axis of the sample, and data from detectors of SEM and from the probe. And this way, afterwards, we remove that slight offset between each of the signals and obtain the CPAM image. So if we have a look here, it definitely shows much more information if we combine it, because here is just the topography, and here is material contrast from SEM. And how it looks like in our software. So it is a web-based software, and as we see, we can have several different channels obtained directly in our control unit. So in this case, topography, secondary electrons, backscattered electrons, there can be local elasticity, magnetic signal, and so on. And so we see the visualization window in the middle, and on the left and right side are the parameters either to be set or monitored. Regarding techniques which we offer, we have 16 different modes for mechanical properties, for measurement of topography, surface roughness, local elasticity or hardness, using different probe. We are able to obtain electrical properties such as conductivity mapping, local surface potential mapping, or STM, or electrostatic force microscopy. We are able to measure piezoelectric domain imaging or magnetic domain imaging. And of course, we can correlate all of the data with the SEM detectors, whichever are available in the SEM. And we have several spectroscopy modes, which you can use either IV characteristics, force distance measurements, nanoindentation, or time spectroscopy. From the application areas which we have the use cases the most, it's definitely material science for low-dimensional materials, steels and metal alloys analysis, batteries, ceramics, or polymer composites. Nanostructures, any modified surfaces, nanostructured films, or nanopatterning nanowires can be measured. In semiconductors, mainly integrated circuits failure analysis or current leakage localization in different ways, either wafers or cross-sections. And from life sciences, measurement of morphology of cells or mechanical properties, measurement of proteins or pharmacy are we are quite useful. But let's have a look at the LiteScope, what it is. And so the first question, what makes the LiteScope? So we have a control unit called NanoBox, where runs the software NanoView. And this part is outside of the chamber. And then the AFM head LiteScope with potential accessories, mainly on the scanner. And so the setup in how we measure the AFM-in-SEM, well, let's, this is the SEM scheme. And so LiteScope is fixed on the SEM stage, meaning potential upgrade of your SEM. Then we need a feed-through for a flange for 2 feed-throughs. which are going cables to the control unit. And then there is connection between the SEM detectors and the control unit. So we obtain all the signals in the NanoView software in our control unit, but still not changing any property of SEM. And then another connection is to SEM computer. So both UIs of SEM and NanoView software are within the same computer. And let's have a closer look at the Nanobox unit. So it was designed and developed and produced in the Brno region with a cooperation with Czech Meteorology Institute, and it fulfills the needs of the market and community. It's composed of open hardware core DSP gyroscope. It has two lock-in amplifiers with frequency range up to 2 megahertz, and it has a high resolution in full range in many external connections for probe excitation or bias tip probe signals. As I said, it's based on the open hardware design. So open hardware is integrated into our product, but it can be it's autonomous operation, so it's is as well possible. So when it's delivered with by us as a LiteScope package, it has full warranty and support is guaranteed for the standard operations. But as it's open hardware, it can be accessed. It's transparent and accessible methodology, code, and electronics, which can be changed. And the nice thing about it is that the know-how is shared between the user community. So academia and industry development is cooperating and can make the development faster. So as I said, there are two phases of Nanobox control unit, one or whole LiteScope package. One, it should be easy for newcomers. So it's a streamlined user interface. It has predefined layouts for each technique. And we have supported the automated functions and AI functionalities for the data post-processing. But it's not closed for the experts. So you can have full control of the microscope without limits. There are 16 inputs and outputs for external connections, and inbuilt scripting module for automation and custom experiments. So there are many possibilities how to use it. LiteScope AFM head is quite small, so it has almost 12 to 8 millimeters in XY direction. Height changes depends on the height of the sample, up to 48 millimeters. And the weight is less than half of the kilogram, with usual working range for the vacuum. Even though a customized version, we have UHV as well. So not only this range, even lower to -8. The scan size is up to 2 to 1 centimeter, with sample height up to 8 millimeters. Our noise floor is 35 picometers. And so regarding the scanner specifications, we have open loop in 100 micrometers, XY direction, 20 micrometers in Z direction. And in closed loop, it's slightly smaller, with resolution XY 0.2 nanometers and Z direction 0.04 nanometers. Regarding the compatibility, we are compatible with most of SEM instruments from all the suppliers of SEM. And regarding the software, NanoView software is a multi-platform web-based user interface. There is no installation of the software needed as it runs in the NanoBox controller. And if needed, it's on the network is created locally, not via internet. So if in your lab, it's not allowed to have the internet on the computer, it's completely fine. There are individual user accounts with customizable layouts and parameters. And we have automatic self-sensing probe tuning functions. So no need of understanding what is happening. We have, if wanted, we have AI-driven automated AFM and SEM image correlation. So again, it's not needed to post-process it manually if not wanted. Regarding the accessories, which can come with the LiteScope package, is a nano case. Such accessory is quite useful if the LiteScope, if you want to use the LiteScope on the table as well, not only in the SEM chamber. It provides a control atmosphere or vacuum, and it has the passive vibration protection. There's sample rotation accessory. This accessory allows several samples or larger samples measured at once. And also it provides the exact orientation if your experiment is, for instance, for the focused ion beam milling, so you can polish one side, rotate, and measure in that range, for instance. Quite new accessory is a sample transfer module, which is semi-automatic for vacuum sample transfers or fully automatic for full load lock systems with a control environment, which are commercially available. So what we see is a loading shuttle and the rails. So automatically the sample goes directly to the scanner. Regarding the nano indenture module, this is a little bit larger accessory, allowing 3-in-1 technique, SEM, AFM, and the nano indenture. The configuration is 90 degrees changed over the standard version. So the sample is on place of the AFM probe, and the AFM probe is where the sample usually is. And the nano indenter is over here from the side. So it allows precise indentation targeting and the result analysis by AFM-in-SEM, thanks to the possibility to measure the topography or, for instance, magnetic properties before and after the indent is done. Let's have a look at the key features regarding the measurements, what is possible. So we have high resolution in full 20 micrometers range. Our z-axis noise floor is within 35 picometers. So what we are having a look is atomic terraces of silicon. And we measured CBAM, so simultaneously AFM and SEM analysis. And what we see that the step height is 314 picometers with 40 picometers. And so what we measured was the roughness of the terrace, 75 picometers. Regarding the conductivity measurement and in general electrical properties measurements, meaning for conductive AFM, IV curves, and KPFM techniques, the current range is 50 nanometers plus minus with noise floor 2.6 picoamps. The bias range is plus minus 10 volts with accuracy 0.3 millivolts. So what we are having a look is the cathode active material sample measured in cross-section. So we see the cathode active material grains here. And so regarding the automated functions, probe tuning is one of them. So as we see, there are just 3 or 4 clicks to measure the, there's one button to tune the probe, and then to get to the measurement, already the probe is automatically getting to the sample, and the last one we started the measurement. So it's really quite easy to get the first image done. From the post-processing automated functions, we have automated correction of AFM artifacts. So if you have trace and retrace of the topography, for instance, you can see that there is an edge artifact overshooting. So using the automated functions, we are able to get the nice image. Of course, if we want it, because for some surface roughness analysis, probably we don't want to interfere with the raw data. And as we have artifact correction, another correction is for the correlation of AFM and SEM data. So if we have the topography and secondary electrons image here, the automated function finds the offset and correlates it directly and places one channel to the other. So it's quite easy, as you can have a look. First of all, calculating the offset of for the correction of artifacts, and we have it corrected. And the second of all, correlation of AFM and SEM data. On the left side bottom, we see how it moved one onto another, and we have the correlated image. So it detected the features very well. But not only the automation, but it has experts have full control. So advanced control possibilities are here as access to all parameters within the systems. There are Python scripting there is Python scripting possible for customized workflow or another automation, and interactive schematics for internal circuitry control. For instance, the external modulation possibility here. And let's have a look at the application examples. First of all, I would get to the material science. So for metals and alloys, in this case, duplex steel, these materials are widely used in oil, gas, or pulp paper industries and many other applications. For that, so we can use it well. Multimodal analysis is important to understand the structure. And so what we see here is a polished surface of duplex steel in BSE. So we see nicely the grain structure. And what the MFM analysis of the white square showed us, it revealed a ferrite grains with magnetic domains and a various intensity of non-magnetic grains of austenite. Surface potential map visualized a surface, KPFM visualized a surface potential and revealed a corrosion tendency of phases and precipitates, or as well some impurities can be revealed quite easily. AFM shows us the real surface topography, and easily we can correlate the data repeatably and fastly locate the area of interest and measure more times if needed. And so this way, comprehensive analysis of AFM-based methods and SEM-based methods is possible. Similarly, for the two-dimensional materials, we measured a molybdenum disulfide flakes of differently grown samples. And so SEM partially shows us the morphology and is used for the localization. The AFM shows us surface topography very well, that it touches the surface. And as we can see in SEM, it didn't look that dirty, but AFM reveals completely different information. And next, we tested electrical properties by electrostatic force microscopy. So we confirmed the information about this material, and further we tested mechanical properties by phase imaging. And all of these techniques we measured using only one probe during one scan. So it's quite powerful. But more interesting was the comparison of these two growing processes. And what is important to say is that molybdenum disulfide has catalytically active edges. So phase imaging helped us to highlight these edges. And what's very interesting is that for different growing processes, the sample grew differently. The first one, there were more layers and concentric nucleation. And in the second type, there was less layers and the nucleation was independent, as we can see here by red. So comparing these two samples with different growth conditions clearly shows where the monolayer started to grow and clearly show the differences in morphology. So afterwards, we could get back to quite dirty topography, as the impurities were more than 12 nanometers high. And so monolayer is hard to see at that moment. And we could do the height profiling on that side. If we move on to the life sciences application, morphological characterization of cells by AFM can reveal novel cell features or understanding the cell scaffold interaction. And so, as many of you probably know, collagen scaffold is extremely difficult surface, as you can see over here. So it's very hard for the AFM to locate the cell and get the tip there. So SEM helped a lot finding such cells and navigate the tip easily and safely to the location. So we simultaneously acquired the AFM and BSE and obtained the CPAM image. And further, we continued with the force distance spectroscopy measurement. So we were able to determine the elastic properties or elastic and plastic deformation of such cells. Further, we could measure the membrane roughness as visible here, which is an important cytological parameter. So if we move more to the ceramic engineering, the surface of ceramic powder particles is quite often analyzed, as it determines the structure and microscopic properties of ceramic compound afterwards from the powders, as there are many steps before the device is ready. So the surface properties affect sintering process, flowability of the powder, and other properties. And why is it studied? It's potentially useful in telecommunication, environmental, and dental products. So our question was, what is the surface roughness of initial powder, and how does the ceramic powder surface change by the calcination process. So from the overview, before and after the calcination process, we don't see much. But if we get closer to the powder particle, we see that already the surface changed quite a lot. So what's the difference between raw and calcinated powder? Raw powder has superior sintering properties and better aging properties, but calcinated is easier moldable, higher flowable, and less compact. And so if we have a look at the at the measurement itself, we could easily navigate and locate the particle, navigate the tip above it, and afterwards we could approach, as visible in the tilted view. We see the very end of the tip and the powder particle on a carbon tape. And afterwards we could do the AFM scanning. So after the scan is done, there is a built-in software for determination of roughness. So there's background correction, area selection for the calculations, and the roughness calculation itself with the easy report export. But let's see what we got. So when we compare the raw and calcinated powder, interestingly, root mean square height was not that much changed, but the developed interfacial area ratio changed quite strongly. So what it means that there was a similar surface roughness, same number of peaks, same height of the peaks, as we can see, there's a same scale, but there was much larger surface area per same distance, as you can see, smaller peaks within the roughness, within the morphology, which well corresponds with the already known less compact, higher flowability of the calcinated powder in the macro scale. If we move further to the polymers, let's have a look at the basic polymer HDPE. As we know, such samples are not so conductive, so they are charging a lot. And they are used for the e-beam lithography resist development, or they are used as e-beam lithography resists. And so it's important to understand the interaction of electron beam with the polymer. So what we did, we first of all used the e-beam to expose a pattern on the HDPE surface, and afterwards perform the phase imaging. As we can see, the harder and less hard properties. And afterwards, as you have a look, we have the SEM overview after phase imaging. So charging is visible quite a lot here. And so what is the trend? What do we see? So we did a statistic of force distance curves. The blue ones are the exposed area, and the red curves are outside the exposed area. So the curves, already by looking, they are quite different. And if we have a look at the trend, which is here by strong red and blue color, we see that a lower stiffness is at the non-exposed area, and it's more plastic. And the higher stiffness is in the exposed area, and additionally, on most places, there was a crack. So it means that a thin, lower probably lower than 100 nanometers, hard crust forms on top of the irradiated polymer. So this crust is breached abruptly by the probe during the indentation, and that is the crack. And so if we continue to the a slightly different experiments which we've done and which we develop, let's have a look at the measurement workflow for cross sections of the samples. First application is on battery structure. We're going to have a look at the lithium-ion battery with liquid electrolyte. And we are looking at the tape, which has anode, separator, and the cathode. And what we're going to measure is a part of the cathode tape, which and what we see here is a compacted cathode mixture with aluminum current collector in between. And so in order to understand the experiment, our conductive AFM is connected in a way that we connect the collector and the probe. So depends on the needs, you can bias the probe or the sample, and then measure the other one is on the ground, and we measure the current between them. And so what are the challenges in these samples is that they are air sensitive, they are quite complex, and they degrade very easily, either on air or by cycling. And so new materials and new components are measured. And for understanding these, the in-situ approach is needed. So there are actually two ways how to measure such samples. First of all, ex-situ preparation using sample transfer system. What it means is that we unbox the tape in the glove box, so it's in argon atmosphere, never have been on air. Then we use the sample transfer system to place it into a cross-sectioning machine, either the SEM with FIP or broad ion beam polisher. And then we transfer it to SEM with LiteScope for the conductive AFM and EDS analysis. The second option is slightly easier, but more for smaller areas of interest. So again, sample is prepared in glove box, moved using sample transfer system, and further sample is polished directly in SEM with LiteScope by focused ion beam and measured by conductive AFM and EDS. As I was talking about sample transfer system, our modular solution is with the loading shuttle, which is compatible with leading SEM inert atmosphere sample transfer systems, such as Clean Connect from Thermo Fisher or Quick Lock from Quorum. And so we automatically place the sample to the scanner while LiteScope is already in the SEM chamber. So the sample is never on air. And so what's the application? We were interested in in-situ analysis of mixed cathode active materials. So the question was identification of mixed cathode active material and electronic conductivity differentiation according to different CAM particles. And also if there is any failure in the device. So this way we put the sample inside and we analyze the EDS first to know what we have. So as we can see, the cathode tape, here is the collector. It's very bright aluminum visible, and we don't see the grain of NCA, nickel, cobalt, aluminum, because aluminum has very small amount of aluminum there. And but thanks to manganese, which is quite strongly visible, we can just say that these are NCA grains, and the red ones are NCM. So from the top view of SEM, we can see the collector, the cathode tape, which is quite a thin film, and over here is already a surface um, of the tape and air or vacuum. And on the top, we see the tip. And if we have a closer look, we see the measured area, which was measured by EDS, so we know which one is NCA and which one NCM, and we measure the conductivity. So as we see, the conductivity is quite stronger on the NCA grain than on NCM, which actually reveals 3 orders of magnitude, and it's more than expected and possible from the theory. So we had a closer look, and we see that here is a delamination happening of the NCM grain. And so we had closer look how the conductivity went. And seems that because here is a carbon additive from EDS, seems that the current was flowing via NCA to the NCM. So such complex understanding would not be possible without the AFM-SEM and EDS analysis at the same time. Further, we could correlate the data. So we obtained all these 4 topography, material contrast by SE and chemical composition and the conductivity. And we can place them on top and see more complex information. And so regarding the semiconductor research, In-Situ site-specific AFM-in-SEM analysis is very useful for current leakages, fails and defects, or potential visualization. So our samples are usually prepared in cross-section or as TM lamellas. We see a TM lamella with AFM tip approach. So you see that it is very precise. And so first of the applications I'd like to explain is the defect analysis of CMOS type chip. So we can see the tungsten plugs. They were polished in a cross section. We can see as well curtains, and the interest was in a surface potential. With the surface potential should alternate on the exact values, but as we can see, it alternates, but on very off values. So there has definitely been a defect in the structure. That it was probably the reason why the structure didn't work. And so a little sneaky peek, I would say, for our development right now. We are working on a MOSFET high power transistor mapping. And so we are able to measure the conductivity and resistivity of the polished surface MOSFET. So we can see even this tiny layer of oxide. But I like to just show what's going on, but explanation you can see in another webinar or at ISTFA this year, ISTFA conference this year. Regarding the recent publications, there are quite many. What you can have a look if you're interested. And I'd like to explain 2 of our customers' applications. The papers has been lately accepted. And so one of it is from the cell life science application is you can see a wild type cell and yes, associated protein, which is a key component cell, but the protein is a key component of a cancer cell mechano sensing apparatus, and it is quite extensively studied for understanding the cell nanoparticle interaction. So very much is study deformities, size, shape differences, surface roughness differences, because if we understand these interactions, we could be able to cure the cancer in one day. So, and you can see the statistic that the wild type the roughness is quite smaller than the ES-associated protein cell. And the second I'd like to say is a paper from Iveta Ukroptsova, and she studied the electron tractor beam, how the beam can move the liquid droplets of gold germanium alloy, and how she can manipulate it with these liquid droplets using electron beam. So when she scanned the line scanned by e-beam, it created this way. And as we can see in the topography, directly there has been quite a change also in the height profile. So definitely there are much more experiments if you have any question in any different research field. Don't hesitate to write us. We Regarding our local partners, our office is here. We have local partners across the world. Our reference laboratories are in Kisjeonbuk in Korea, in Arizona State University, in Arizona in US, in Prague in Czech Republic, and in Technical University Munich in Germany. Further, you can find more applications and product information on our web, or we post regularly on LinkedIn, Facebook, Twitter, or on YouTube account. Or you can reach us regarding your field of interest, either me or Thomas. Where we're gonna be, you can meet us at conferences. First one will be at EMC in Zakopane in Poland. We're gonna be at M&M in late July in Cleveland, or the same name EMC in Copenhagen in Denmark in late August. Swiss Battery Days at the same time in Zurich, and the Faraday Conference in Newcastle upon Tyne in UK, ISTFA in San Diego in US in late October, beginning of December. So if I should summarize what we've been talking about, I explained the main AFM-in-SEM technology, how it works, and what are the main benefits as in-situ characterization, correlated multimodal microscopy, and precise location to the region of interest. I introduced the key features of LiteScope package, and it's that it has ultimate performance inside your SEM. It's upgrade, so you don't have to buy whole SEM, but you can put it there, install it there when you need. And it has 16 measurement modes for mechanical, electrical, magnetic, and chemical properties. There are many optimized workflows and easy to use operations. And as we are based on open hardware design, many experiments are possible. So regarding the applications, application examples, I did, let's say, overview of what we have, but there are many more which I didn't have time to go through, and there are many more of new experimental designs, either of e-beam use or controlling the experiment. So with this, Thank you for your attention. I will be happy to chat to you, to answer any email question you might have. And thank you.